The geologic timescale was originally a relative age calendar for Earth's geologic history, where one thing related to another. The names on the geologic timescale, many of them are place named for the type locality of different units, or they're kind of the Latin version of things um, related to geologic time. Go from the broad eons down to the less time unit, the epochs. Okay, so here are the eras of the Phanerozoic, Cenozoic, Mesozoic, Paleozoic. Those are in the Phanerozoic epoch, and these are the eras. So Cenozoic, Mesozoic, Paleozoic. And what I was saying about the Latin word for something like Paleozoic would be old life, Mesozoic middle life, Cenozoic new life. These eras are separated from each other based on things related to the evolution of life. So between the Precambrian and the Paleozoic, this is where the beginning of hard-shelled organisms. So in the Precambrian, they were mostly squishy. Precambrian, above that, we had hard shells. At the end of the Paleozoic is what's called the Great Dying, and this is where most of the organisms in the ocean died, like trilobites, for example. Then we had the Mesozoic and the evolution of dinosaurs, and the end of dinosaurs marks the end of the Mesozoic about 66 million years ago and the beginning of the rise of mammals in that era. Okay, let's expand the timescale a little bit here. Boom. Okay, so what we just looked at was the time periods in here in the Phanerozoic. So everything before the Phanerozoic is Precambrian. In the Precambrian, there's the Proterozoic, Archean, and Hadean. So the Hadean is the beginning of the Earth 4.6 billion years ago. Okay. The Cenozoic is the time period we're in now. And go across the diagram over here, we are in the Quaternary, and in the epoch we're in right now is the Holocene. Just before that would be the last ice age, the Pleistocene ice age. So we've expanded out the Phanerozoic eon here, the different periods, and like Jurassic Park, this is the Mesozoic, the time in Jurassic and Cretaceous of the dinosaurs. Okay. The Cambrian, Ordovician, Devonian, that's like the explosion of organisms in our ocean basins. All right. So here is a breakdown of those bigger units, the eons. The Archean then is here at the beginning, 4 billion years to 2.5 billion years ago. This is when our atmosphere was starting to form, climate was set in motion, plate tectonics started, where we started to get solid continental crust, and then our ocean basins were forming and continents were colliding. So the oldest rocks record that early history of plate tectonics. And we started to get the very beginnings of unicellular microorganisms. In the Proterozoic, organisms got a little more complicated. We started to get those stromatolites. The rocks are 2.5 billion to 543 million years ago. Oxygen was forming, and so this is where we had the precipitation of iron oxides in our ocean basins. The Phanerozoic is the bloom of life, and it's the past 543 million years. So many fossils. Those fossils led to the formation of our hydrocarbons, the oils and gases, and then that Phanerozoic is split into that Cenozoic we're in now, the Mesozoic, the Paleozoic. So that's an explanation, just quick, of the geologic time scale. Later, after the relative dating of the time scale, we could put ages on it with isotopic dating. So in 1896, Henry Becquerel, he found that uranium was radioactive. That same year, Marie Curie discovered the radioactive element radium. So that was in the late 1800s. In the early 1900s, scientists were like, wait, if we have these radioactive isotopes, ions, and they're falling apart over some amount of time, could we use that to date rocks? So right around the turn of the century, there's when it was realized that indeed, yes, we could use isotopes to date rocks. Okay, so how does it work? Some isotopes are stable, like oxygen. Yay! We're breathing it and we're not like exploding or burning or getting cancer. But some isotopes are unstable, so their nucleus spontaneously disintegrates, and that produces radioactivity. Isotope just means that atom has a different number of neutrons in the nucleus, and some of that's stable and some of it's not stable. So the idea is that a isotope, a mineral, is going to crystallize with a certain number of parent atoms in it, and those are going to decay over time into daughters. So the example here is rubidium-87 that decays into strontium-87 over time, and in doing that, it's going to do it by half-lives. So a half-life is if you have a certain number of those rubidium-87s, over a half-life, half of them will be turned into daughter atoms. So if we know an isotope's half-life, we can look at the ratio of parents to daughters in that mineral and determine the age of that mineral. Okay. So the half-life for an unstable isotope is a fixed number. So it can be thousands of years up to billions of years. Once a half-life has passed, then half of those parents are going to remain, and we'll have half daughters, and then half again, and then half again, and half again. And so knowing the rate and the numbers of parents and daughters, we can figure out when that mineral crystallized from a magma. That's when the geologic clock was time equals 0 for that mineral. There are specific isotopes we use with different minerals. So not all minerals can be dated because they're not all going to have these unstable isotopes. But here's some useful ones. So if we have a mineral zircon or apatite in a metamorphic or, in an igneous rock, then we can use uranium lead, or the U-238 or the U-235. If we have muscovite, biotite, hornblende, those we can use potassium argon dating, and then muscovite, biotite, potassium feldspar, rubidium, strontium. So different systems are used with different minerals. So you have to have the right mineral in order to use that system. Another one I'm sure you've heard of is carbon dating. So this is C14, and this is dating organic material. C14 decays to nitrogen 14, and the half-life is kind of short, 5,730 years. So we can use it on material that is a few tens of thousands of years old, so relatively new organic material. And some of the examples of that organic material, so anything that's been alive, wood, charcoal, peat. We can actually date seawater, glacial ice, groundwater, anything made of calcium carbonate like seashells. And this material is going to be found in sedimentary rocks. So if we date like pollen in a sedimentary rock, that would tell us the age of deposition of that sedimentary rock. This is used a lot in archaeology. All right, there are some limits to isotopic dating, right? I was listing off some of the minerals that have the isotopes in them that are useful for dating. So if the mineral's not there, it can't be dated isotopically. So you have to look for the right minerals. I misspoke about metamorphism earlier, but so with metamorphism, during the recrystallization of minerals that happens with heat and pressure of metamorphism, it resets the clock. So you're typically not dating the age of the rock, you're dating the age of metamorphism, but it's tricky. So you have to do a lot of background research before you can get that metamorphism age. Weathering also alters isotopes. So if you have a rock, I have one right here. If you have a rock, you would need to knock off the outside of it and just date the minerals on the inside, and you could take off the weathered rind of it. Minerals are also really small and hard to isolate, so a lot goes through processing a chunk of granite to turn it into something that is, let me go find a granite. Hold on. Okay, I went and found a granite in the yard. This is a rock that my kids picked up out of a stream in New Hampshire 2 summers ago. So in this rock, you see all the little minerals. What you can't see are the zircons. So those are the general size of minerals in a granite, but the zircons would be so small you wouldn't be able to see them with your naked eye. So they're hard to isolate in something like this. With sedimentary rocks, if there's no organic material, it's really hard to date that sedimentary rock. We really hunt for fossils in order to determine the age of that rock. Okay, so in this stratigraphic column, there's some fossils in here, and what they're able to date is the volcanic ash. So isolate minerals in the volcanic ash, and then you can date those trilobites and these bivalves here. Okay, so here's a sequence of sedimentary rocks. We may not know the ages of them, but what if we can date that volcanic layer, then we can kind of bracket the age of those layers. Here's another set of sedimentary rocks, and in this one, maybe there's some fossils in a layer, some a dike that cuts across those layers. We can date the dike and we can date the volcanic layer, and that will help us kind of get an age range for those sedimentary rocks.